Celia. All right, great, perfect. So Celia Chen graduated from USC in 2019. She's also one of Dr. Bame's alumni. She's on sabbatical from Occidental College and is currently working at Posh Technologies as the principal engineer.
All right, awesome. Thank you. Can you all hear me? Yes. I'm gonna
Yes.
peek over. Okay, great. Okay, so as you can see, I don't do research in Kokomo, but very happy to discuss afterwards to see the type of work that I do in AI and natural language processing to see how that can be maybe utilized in Kokomo 3. So I'm sitting through these discussion. So this is a work that I've collaborated with a bunch of our old friends in the Institute of Software at Chinese Academy of Sciences. In fact, Dr. Shi was one of our visiting scholars at, with Dr. Bain. So this work was presented and accepted at HCAI this year. So what we really did was sort of improving this area of dialogue and disentanglement, specifically in the software development type of environment. Okay, I have some time, so we'll make it quick. Then we can have some time for questions if you have questions. If not, if we don't have time, feel free to email me afterwards. So give you a little bit of background in terms of what we're doing. So basically there's a lot of online communication platforms that developers use to discuss with each other. So many of the open source software developers like to share their issues or concerns on this platform called Gitter. So the way to think about Gitter is it's basically a Slack, but it doesn't really have channels, right? It also very difficult to have thread because you kind of lost track of things as you have like thousands of developers constantly communicating at the same time in the same room. A lot of times what we see is there are a lot of data, but these data are mixed and they're only organized by timestamps, which means some of the dialogues may be mixed, right? I don't know who is answering whom. I could be answering you, but I could also be answering like someone like 20 messages back. So that comes in this sort of area called dialogue disentanglement. So here's an example, right? You can see speakers are talking about Angular JS bundling and Tomcat PyCharm. So those are two different topics, right? But we cannot directly figure out what they're talking about when only analyzing these utterances. Okay. However, if we apply any type of dialogue disentanglement model, then we can sort of disentangle them or separate them into dialogue 1 and dialogue 2. Now we have better understanding of the topic of each of these conversations. Okay. There are a lot of existing approaches for this. Mainly, there are two very big ones. One is what we call utterance to utterance prediction. So what this does is it embeds the utterance and predicts whether two utterances have the reply to relationship. Therefore, you can decide whether they should be sort of clustered into the same dialogue or not. And the other type that's very popular is called utterance to threat prediction. So this model uses the embedding of dialogue threats to directly predict which dialogue the utterance belongs to and updates the threat embedding as you go. Okay, so you can see it's kind of two different approaches. Okay, and you have sort of the hybrid prediction model where it incorporates both of these predictions. But one of the sort of drawbacks of these existing hybrid methods, they often train the two models independently, which meaning the stuff that each model learns cannot be shared. So that's why sometimes it actually doesn't really help you to improve your model performance because knowledge is not transferred between, or it's not shared between the training process. So couple of things that we want to improve. First, we want to use user intents. So basically, here is an example. You can see that utterance number 6, right? And says you can try rebooting your app IDE to fix every breakdowns, right? So the utterance number 6 is usually disentangled with utterance 5, okay? Because it's the same speaker, speaker 3, okay? Right. And also it has the same keyword app, but we know that 5 and 6 are talking about different things, right? Okay. So what we're trying to do here is if we introduce the user intent here, we can then use the prerequisite knowledge. For example, the utterance with information giving tend to directly answer the original question. And if it answers sort of belongs to the information request, it needs to contain the entities like screenshots, files, and so on and so forth. Okay. So that's why we thought, oh, maybe user intent might be a good parameter in disentangling these dialogues. Right. So you can see these are sort of the different type of these dialogues. You have greetings, questions, information giving, information requests, and so on and so forth. Great. So yeah, so sort of being motivated by these two things, specifically, having hybrid models that don't share learning outcomes and not using user intents in disentanglement models, we came up with sort of our model, right, MuiDial. So given a chat slice with utterances, all right, that's our input. We want to first use the pre-trained, basically, BERT model to embed the word sequence into individual utterance embedding. Then we enrich the utterance embedding with some high-level heuristic features with, for example, speaker information, time differences, topic, entity, mention, relationship, so on and so forth. And then we introduce this, what we called user intent encoder to embed that intent. So we have some predefined intents from an empirical study that we did the year before. And with that, we output a 6-dimensional weight of the intent embedding. So we also use softmax activation to output the probability of that intent classification, so we can classify it, automatically given a utterance. Finally, we concatenate all 3 of these embedding and use a context-aware encoder to output the intent-based utterance embedding, which then we use to do prediction. There's going to be a lot of math. I'm actually going to kind of just explain this in a very sort of high level without bore you guys. But if you're interested in to see how the math actually works out, I have the code that I can share with you. There's also plenty of math that's included on this particular slides. Okay. All right. So let's see. Cool. All right. So this part is basically our intent-based utterance embedding. So you can see that in here, what we're doing is with that chat slice, we are outputting, sort of a embedding using a pre-trained BERT model. And with that, what we're doing is we're also adding on top a heuristic feature encoder, which enriches the embedding with these different high-level semantic features. For example, who are the speakers? What are the time differences of this particular utterance versus the start of the chat slice? And topic, so top 10 words for dialogue topic that we extract. Entity is also something we extract. And mention as a number of this particular speaker, right? Mention other speakers. So basically what it does is that at the end, you have a concatenated embedding where it contains all of these information that we extract from this encoder so that we can pass it into the next encoder to continue encoding. And these are the categories of the user intents. So we label them, and those are right now automatically trained, right? Before we had to label them and trying to figure out what they are. So we have things, for example, original question. So speaker proposed the first question to initialize the dialogue, and there might contain follow-up questions. There might be information that the speaker is providing to other speakers. And it also, the speaker might also seek additional information from other speakers, and the other speaker might, so the speaker might also provide some sort of feedback to the solution proposed by other speaker. And there's other type of things that says hello, goodbye, and so on and so forth. All right. Okay. So, and with all of that information at the end, as what I was just saying, there's a context-aware encoder, which takes all of these information we talked about, right, to output the intent-based utterance embedding. So we, at the end, have sort of embedding matrix that we can use for future work, for future steps. Cool. All right. So, well, the second part with that embedding, we now propose two different sort of models. So those are the two things that we talked about earlier, where you have utterance to utterance prediction, utterance to thread prediction. So we propose these two different prediction models, okay? So basically for this utterance to utterance prediction, we build a probability matrix to describe the reply to probability of these different utterances. It is what we call a lower triangle matrix. Okay, so that's what we're producing. So that is our triangle matrix. And then we propose sort of a dot product. Okay, let's see if it's on the second page. This is, there we go. Then we propose what we called a dot product measurement to measure the similarities. And then we're selecting sigmoid, sigmoid activation to calculate the actual probability. So what this actually gives us is a probability of whether these two utterances belong to the same dialogue. And you have the second type, which is utterance to thread prediction. So in here, we're using the state transition to measure the belong to similarity, where we basically build what we called a K states. So this right here, you have to the K, and choose the dot product to calculate T, right? The belong to probability. Then we use the self-attention to update the session states. And here is our belong to probability matrix. Right. Okay, cool. So since the mutual learning requires to optimize model with two same output probability, you can see how the probability matrix we output may not be the same dimension. So we actually need to transform them into the same dimension. So that's where we use this thread-based transformation to transform our belong to probability to this sort of same, lower triangle matrix, which we call this thread probability. So with that, then we can apply this technique in AI, which is widely used in some of the other fields, which is called mutual learning. So the way mutual learning works is it shares learning parameters, or it shares learning outcomes between different models, okay? So that means whatever we train from the first one versus what we train from the second one, the parameters, the outcomes, the learnings are all shared. Okay, cool. All right. So what that takes us, I'm gonna hurry up, okay, because I have 5 minutes left. So in order to apply this mutual learning, we have to calculate the loss of intent classification and all of these the two prediction models as well. And then you have to calculate sort of the KL loss between the two thread probability. So with that, we came up with a optimization function where we use the cutoff value of 0.6 to determine the predicted probability in the test dataset. And we choose sort of the vote and struct way to gather the utterances into disentangled dialogues. So that's pretty much sort of how the model works in general. Again, it's very high level. There's a lot of details that I'm skipping, but if you're interested, please hit me up afterwards. Happy to share more details. Okay. With that, in order to evaluate, we actually did a couple experiments with these benchmark dataset and dialogue and disentanglement tasks. And with a couple, sort of standard evaluation metrics. And what we found out is, I'm just gonna let you read that on your own so we can talk about the performance. So one of the things that's kind of interesting is performance of intent classification. Remember the part where we talked about using user intent? So here is some, diagrams. You can see the coverage analysis of intent classification during training of our model. So we can see that the intent F1 score can actually reach relatively high. So it's actually relatively stable and satisfying, right? And our model converges faster than regular intent classification model. And so yeah, so since our model can achieve the highest performance when the intent F1 score are around 55%, we believe that the current intent classification is good enough, right? Using a better intent classification model may not upgrade our performance any better, okay? So let's keep going. Cool, great. So yeah, so here is the performance, the analysis of these hyperparameters, right? So so these are things that we have to select when we where we have to define when we incorporate or when we train these two models using mutual learning. So these just basically these were the different, I guess, alpha and beta values for that for the training model, right? So during the process, we also realized that the bigger K gets, the value of one of the matrix show a positive correlation, but the growth is very slight. Okay, all right. So what did we learn from doing this? Well, first we learned that a lot of times model improvement will give you slight outperformance, right? Slight improvement. So in this case, evaluation on these 4 benchmark data sets show that our model outperforms the baseline by about 5% on average. Okay. So we also proposed a very sort of the first model in all of the dialogue disentanglement models where it based on intent. And we also use mutual learning, which allows you to parallelly train 2 different models and share the learning outcomes and parameters with each other. So yeah, so oh my God. Oh yeah, I forgot. Sorry guys, I gotta scroll. All right. So what do we want to do, right? Currently, what we're doing is right now, what you can see is all of these code related text we are removing. So we're doing these dialogue disentanglement solely on natural language, basically things in English, but we're ignoring these specific sort of code fragment and stuff like that. So what is the contribution of these specific text fragment? That's what we are trying to figure out, right? So here is a very good example where you can see the raw dialogue has these like Java error messages. But after we process that, we literally just remove the entire thing, replace it with code, okay? Right, so in this case, what we can see is we're losing information that can be used to map U1 and U2 into the same dialogue, okay? But in this case, whatever we have right now, these two will very unlikely to be mapped into one dialogue because of the missing information from the code fragment. So what we're doing right now, we're trying to introduce some keyword analysis on these fragment pieces, right? Whether it is URLs, code, prior to data pre-processing to see if we can extract some levels of information that we can use for our training purpose. Okay. All right, cool. So yeah, so that's a very, very quick, I know I flew through the slides. Yeah, so what we did right here is really just improving on the existing work of disentangle dialogues, specifically in the software setting, right? And we were able to use a very novel approach to approach the problem and to understand a lot more about user intent, about the actual meaning of utterances before we tend to pair them up or tend to classify them into the same topics. So yeah, thank you very much.
Any questions or comments for Celia? No?
Awesome.
All right.
Great.
Well, thank you, Celia. That was a really interesting presentation, and thanks for being so prompt about it.
Yeah, of course. If there's anything I can help with Kokomo, with AI, or NLP related stuff, feel free to reach out because that's the type of thing I do right now.
Okay, that sounds great, Brad. Just keep that in mind.
I will.
All right. Thank you again, Celia. So
Thank you, hon.
with that,